Alright, we're going to see whether this works. It looks like it's kind of screwing up a little bit, so we're going to go ahead and try this PowerPoint. Well, I'll ignore this out over here for now. That does not look like something you want. Alright, so we're going to look at it. One of the more simple problems when you're trying to think about these things, even beyond a simply supported beam, is something that's got a fixed end moment or a cantilever, a pole more or less. It helps you kind of really quickly figure out how stresses are working within. It's something you should be aware of. You know, all kinds of places in the world where these exist. So let's assume you apply a force to one. Then, of course, based on equilibrium, there needs to be an equal and opposite force and an equal and opposite moment, which you have worked at doing graphically. If you remember, you can slide a vector along its line of force and not change the mathematics of equilibrium. If you slide it parallel or perpendicular to its line of force, you need to add a moment equal to the force times the distance that you move along that perpendicular line, or more or less the area that you swipe, if you would, with that vector. Okay, then you can, once you do that, and even without solving for the reactions, you can always cut a section at any one point and then reapply those same rules of equilibrium. Okay, so if you think about right there, if you cut your section right there at the force, right at the same spot, there'd be no bending moment, and you just have a cable pulling on a cable. But as you go down the structure, right, that bending moment is going to grow until it hits its maximum. In this case, down here at the bottom, where you have essentially would be a critical section. And when you look eventually at the mathematics of this, you can see that at the very top, there is no bending per se. It's just it's bent out on the end, but there's no curvature to that beam. The maximum curvature in this beam is going to be down there at the bottom. That said, what actually is occurring in the beam? And this is where we may run into some problems with that little piece of problem on the left, but we'll just live with it. Right there you have how the axial forces, P over A, distribute all the way evenly across the face. You have then the shear forces, which are, these are the two components of the forces across the face and perpendicular to face. Those are the definitions of shear and axial force. They have to do basically with relationship to a plane. And I point out there that whereas we know basically that the allowable axial stress is going to be a function of whether it's in tension or compression, in other words, how it might buckle based on the slenderness ratio KL over R. We know the actual stress is P over A for axial, and we know the actual stress distributes oddly across the face for shear, equal to V, the shear force, times the first moment of the area divided by the second moment of the area and the width. But realistically, we very often use an allowable 40%, and so we just use V over A. And then we notice then for concrete, as opposed to relating things to the yield stress, we relate them to the compressive stress, and that factor is a lot less than 40% typically. And you notice there, it's not a multiplication of the number itself, but of the square root of the compressive strength. So that's a key thing to realize, that when you're doing concrete for PCC, you're not multiplying your factor by the yield strength or the compressive strength, it's by the square root of the compressive strength. Of course, that shear stress is actually, stress times area is force, and that shear and the axial stress times area is force, axial or shear stress times area is force, and you have that equilibrium developed there. In addition, of course, you have the bending. And we remember that with bending is foot-pounds, but those foot-pounds are actually equal and opposite forces that are actually not forces now. We start to look at they are actually stresses that distribute unevenly across the face. And so you have this concept of the bending stress. The maximum bending stress, either on, maximum distance away from the neutral axis, is going to be equal to m over s, when of course s has units of inches to the third, and s being equal to the second moment of the area divided by the half depth of the beam. You have compression on one side and tension on the other, which combines with in this case, the compression along the whole face to get something called a combination stresses. And we want to realize that basically we are interested at any point in the beam sometimes. So if we want to know the absolute bending stress at any one point, which just exhibits something like axial stress, it's equal to m over I divided by or multiplied by the distance from the neutral axis. which makes then some sense. Maybe when you go and add those two together, you get actually a neutral axis that actually is shifted from the center of the beam, because you've got essentially the compression due to the axial forces adding to the compression due to the bending, and then the tension forces adding to the compressive forces along the other face or the other half of the beam, which means you just have less tension. And essentially that's what you're often doing when you're doing pre-stressing of concrete. You're actually applying a faux axial stress of compression along the face of the beam. Of course, this all leads us back to the fact that stresses are combined vectorially by using Moore's circle, and we don't need to delve on that just to realize that any one piece of a beam, cross-section of beam, feels a combination of stresses. But we do need to know that even though we start with looking at stresses and purely just looking at the area, for in other words, area is its resistance to force, and then moment of inertia is its resistance to torque, we do eventually transform the sections by expanding the stiffer material. And we'll be looking at that in the coming weeks. We have in the past as well. So we're going to more or less have these ratios. One in our head is about 9 or 10, the stiffness between concrete and steel. And so we're going to expand the steel 10 times when we do our mathematical calculations, and then flip it back when we want to know the actual stress. All right, so here's what we generally do. Why we spend so much time adding vectors in many, many different ways, including graphically, both by hand and by AutoCAD, mathematically using basic vector mathematics, using calculators, using spreadsheets, using logic, using graphics, and here's why. We need to determine the critical sections where either shear is either at a maximum for worrying about the actual shear forces going, or shear stresses going across, or even sometimes more importantly, where the shear is zero, because where the shear is zero, the moment will be at a maximum. We draw a free body through that section or sections. We then pick a member that allows us to solve this equation M over S or V over A based on the criteria of either 60% or 40%. So we're going to be selecting a beam, solving for S, section modulus, and then selecting a member that works, or solving for A and picking a column or a tensile member for P over A and then for V over A as well. We check for deflection. In other words, we do not want these things to deflect too much, and very often you'll see deflection is going to be what, in effect, ends up sizing your member. So your actual stresses will be much less than what's allowable, but in terms of keeping deflection at some percentage, basically the span divided by 360 or the span divided by 480, you're going to end up selecting your member. Additionally, you need to recalc for the additional self-weight. Remember, the distributed weight of a beam, a W24 by 65 is 65 pounds per foot. And that is distributed. It is not, of course, it is not a point load. And so for that case, if you need to know, for instance, the maximum moment that's added by the self-weight, you just take the 65 times the span squared divided by 2, WL squared over, divided by 8, WL squared divided by 8, and you'll see that WL to the fourth, and another number comes up when we start determining for deflections. And then finally, we need to assure that we do some cross bracing so our members do not laterally torsionate buckle. All right, so this gets us to this, I'm not going to call it a summary, but a comparison of the mathematics of F equals ma, torque equals I alpha, and the integral mathematics of the fact that the shear is equal, at any one point in the beam, is equal to the initial shear minus the area under the load curve. And what you have to realize is when there is a point load on a structure, that actually just adds a kind of it just kinks your curve. It comes straight down along that point load. The moment is equal to the initial moment divided by the area under the shear curve, and then your actually deflection angle, right, is going to be related to an area under the moment divided by the resistance to spin, or the resistance to rotation, EI. E having units, of course, of PSI or KSI, and I having inches to the fourth. You see how this stuff, mathematically, it does relate. And that is why we spent so much time on thinking on area under a curve. That's why we take pounds per square foot and put the square foot on the bottom. These things are to be taken from mathematics and physics and applied and generalized based on the math. Thanks for listening. We'll see how we apply it in the next couple of weeks, including we're using Revit, using Inventor, and using just base calculations. Thanks for listening.